Okay, so let's do a example with single slit diffraction. So let's imagine that we have a slit here, okay, and the slit is a width A, and let's say that this is 1320 nanometers. Okay. And then on the screen over here, we got a bright spot in the middle. And so the minimum of the bright spot is going to be out here. So I want to shine light on it. So let's take violet light. Okay. So violet light. Okay. So that's going to be a wavelength of 400 nanometers. And so what we're going to do is shine the violet light and see where is the minimum. In other words, how wide is this spot right there? So the minimum occurs, we said, the first minimum, A sine theta, okay, equals m lambda. So m equals 1 is the first one. So sine theta is going to be lambda over A. Okay, so theta is going to be the inverse sine of lambda over A. Okay, so theta inverse sine lambda 400 nanometers divided by 1320 nanometers. Okay, so what does that give us? So we plug in the calculator. And we get that that is 17.6 degrees. So that spot, so the light shining through here, and the angle here from the center goes out 17.6 degrees in either side. Now that's for violet light. What about for red light? So that was violet. What about for red? Red is 700 nanometers. So now we get a different result. So we get 700 nanometers divided by 1320 nanometers. Okay, and so what does that give us? So now we plug that into the calculator. And that gives us 32 degrees. Well, that means that the central part here, 17.6 plus 17.6, so the central part is going to be about 35 degrees, so this is about 35 degrees across, but for the red, it's going to be about 64 degrees across. So that would mean that if white light was shining in here, you'd get violet in here, and then you'd have a little bit of blue and so forth, and then finally red on the outside. So you'd have a rainbow pattern over here, in which the red light is more spread out than the violet light. And so this is going to be a dispersion effect again. We talked about dispersion before, in which the different colors of light the different colors of light travel different speeds in the material. Here they're diffracted by different amounts. And so this actually turns out to be another interesting thing, because when you're looking in a microscope, you might have structures, for example, in an organism you're trying to see, or you might be trying to look at something, like a bacteria. Now, we've talked here about a slit and then having a bright central minimum. The opposite of that is an anti-slit, or Or in other words, instead of having a slit, we have something blocking right here. And then over here, instead of just a dark shadow right here, then the light going past here is going to spread out as well. Does it make sense? And so that means that if the light spreads out too much, then you're not going to see a shadow over here. Well, that implies there is a minimum size object that you can see. So if you got a bacteria or a virus or something and light is shining by it and you're trying to look, if the light comes together on the other side of it, then you're not going to be able to detect that it's there at all. And so there is a minimum size here. So now the question is, well, what would be the minimum size slit that you could possibly get? Because that'd be also related to the minimum size shadow. So if we have a slit here, some width A, and I want to know how narrow can that get and have light still diffract through. Well, the narrower it is, because you look at this and we say, okay, sine theta equals lambda over A, so theta equals arc sine of lambda over A, then what happens is the narrower that lambda gets, or rather the narrower that A gets, then the bigger that number is. That number cannot be bigger than 1. You cannot take the inverse sine of something bigger than 1. So that means this is undefined once lambda reaches A, or rather once A reaches lambda. So that means the shortest thing you could see would be related, the smallest structure you could see would be related to the wavelength of the light. So that makes an effective, an absolute minimum size that you can see. So in a microscope, you're trying to look at something like a bacteria or a virus or something, and you're lighting it from below or whatever, and you got the lens up here trying to look at it. And the problem is, if that object is less than the wavelength of light, well, remember, visual light is 400 to 700 nanometers. Okay, so near the middle of the spectrum is going to be something, like 500 nanometers. So visual light, about 500 nanometers, that's near the middle of the visual spectrum. Okay, so that means the smallest thing you could see would be 500 nanometers. And if you try to see something smaller than that, then the light will diffract around it and you're not going to see anything. You're not going to see the shadow. You're not going to see any structures. So that's the smallest thing you can see. Now, you can hedge that a little bit by using instead of all different colors of light, because this is one problem you have with very small objects in microscopes, is that if you have all different colors of light, that you have different amount of refracting going on, and so you're going to see one color in focus and the other colors kind of like splayed out. So using monochromatic light helps. The other thing that helps is using shorter wavelength light. So in other words, if you were using a blue light instead of green light or red light, then you could see smaller structures. Okay, so that's another strategy. Yet another strategy that you can do is put a drop of oil right here. The oil has an index of refraction bigger than air. So the index of refraction of oil, might be 1.4 or something. The higher the index of refraction, the shorter the wavelength. The shorter the wavelength, the smaller object you can see. With the same color light, is going to have a shorter wavelength. And so this is the principle behind an oil immersion microscope. It allows you to shorten the wavelength that lessens the impact of diffraction around an object and lets you see smaller structures.